Good afternoon. This is CIVE632, Computational Hydraulics and Hydrology. And today is December 1st, 2021. And this is the second lecture of the 15th week. And the 15th week is the last week of lecture. So next week, we're going to have the student presentations. The students have been working on for almost 8 weeks on topics that they themselves have chosen from a list of topics that I gave them. So they should be very well prepared to present next week. So this is the last class that on this the last video, I guess you could say, the last class of this class. It's redundant. These classes, of course, have been posted. 90% of them have been posted on the web, and anybody around the world can take a look at them. And I've received some feedback already. People around the world are looking at these classes or at these lectures. So let's get going in here. And what I'm going to do today, the subject is two-dimensional flow. I haven't talked about this before, and it's going to be thick, meaning involved, technical, very technical. But that's just I get to say the nature of the beast. That two-dimensional flow is a lot more, 10 times more complex than one-dimensional flow. Let me just say this. Let me, while I look at where we are here. Syllabus. Okay, and now I'm going to open up the page. Okay, do you see the green page?
Yeah, we see it.
Okay, cool. Okay, so this paper is a paper we wrote in 1981. Actually, we did the work in 1979-80 with Steve and Yabusaki. Steve was a student of mine, master's student at the time at Colorado State. I was at Colorado State for 4 years as a professor before I came to California. And basically, I hate to put it that way, but this project was, I was the mind and Steve was the legs. Steve was doing all the running around and checking and everything, but basically I had already developed a similar model in other words, I did not entrust Steve to do the modeling completely because it was a difficult job, right? So I spent 2 years actually developing the model, and then we spent 2 years with Steve and Yabusaki applying the model to the issue of circulation in depth average flow. The 2D model, it could be either depth averaged or vertically averaged, but we were interested in the depth average model. In other words, the velocity, the vertical velocities are considered to be constant, one value for the vertical velocity. So there's two horizontal velocities which we are going to be modeling, but we're not modeling in detail the vertical velocity, which is assumed to be a mean value. So how did this work originate? Well, at the time, my mentor and boss, I guess you could say, he was, because it was a group of people, research group, and I was working under, I was young at that point and working under Daryl Simons. And Daryl Simons got this grant to do research on the Mississippi. And one of the topics was to develop a two-dimensional model. So he hired me to do this, and of course I didn't know anything about it, but he gave me a couple of years. He said, you got a couple of years to do it. And in a couple of years, you can do a whole lot of stuff if you know what you're doing. And so we basically spent the years 1977, 78 working on it, and then 79 and 80 with Steve and Yabusaki. Now, what's the difference between modeling two-dimensional flow and modeling circulation? Well, you can see in there, there's a graph that shows circulation. The flow is coming from the left and then going in there and convecting, the flow is being convected inside the pool, so to speak. And it's coming around. You can see the vectors in there. It's coming around and going in forward and then goes in and around, right? That we see that. When we first originated this model, there were two possibilities, either convection or rather convective or circulation. And circulation actually, it could be interpreted as diffusion, and I'll explain that later on. Uh, so, so when I first ran our original model, I showed it to Daryl Simons. I showed everything I was doing to Daryl. He was the boss. And I showed him a convective result, meaning the flow was going in and it was not circulating. And of course, at the time, I was a junior person, and I just said Professor Simons, we have gotten this result, this preliminary result. And he said, well, Ponce, the problem is not like that. The solution is not like that. He said, it does not convect, it does circulate. Because he said that he had seen it circulate in the Mississippi. He had a lot of experience in the field. And I had seen the flow rounding around and circulating. So the solution that I was presenting was not quite correct. There was something in there that needed to be studied. So I researched the subject and I realized that not too many people knew about it. The people that worked on two-dimensional models, but they were not talking specifically about circulation. So then I decided to do a research project. At the time, we were pretty much had to be in the business, in the research. So I presented a proposal to NSF to specifically study the circulation. We were going to take this model that we'd already put together, and we're going to spend a couple of years trying it this way and that way in order to find out what exactly was it that caused the circulation. And I believe we did find it, by the way, and I'll explain to you later on. The circulation or no circulation is a question of scale. I'm advancing to you the things I'm going to say at the end. Just suffice it at this point that there is a question of scale. And with their scale, like in the one-dimensional model, if you recall our one-dimensional classes, the scale is given in our S-curve, the scale is given by the abscissa, the dimensionless wave number. If the dimensionless wave number is small, then that's a kinematic wave. It's a very long wave. You cannot even see that wave. It's too long for you to see. You can perceive it, you can sense it, but you cannot see it. It's too long, right? It's miles and miles. How are you going to see a wave that is miles and miles long? Okay, but when you move to the right of the S-curve, then those are very short waves, because the length, the wavelength is in the denominator. So on the right of the graph is the short waves. And these short waves, yes, they can be presented or produced in the laboratory, and they are the Lagrange waves, and they can be seen. Anybody can see those waves because they're short. The order of magnitude is about 5 orders of magnitude compared to the kinematic waves, because there's 6 orders of magnitude in our S-curve. And those are orders of magnitude, not of wavelength, but of dimensionless wavelengths, which is even better. In other words, we have concentrated everything into 6 orders of magnitude, and we believe that those are the only ones. If you express it in 8 orders of magnitude, one on the left, one more on the left, and one more on the right, you're still going to get the same answer on the kinematic wave and the Lagrange wave, the Southern wave, okay? So 6 orders of magnitude we thought was more than enough to represent the entire phenomena. Luckily, of course, and I've repeated this many times, and I should ask you on the exam, by the way, that it was the development or the discovery of the dimensionless wavelength that gave us all that information and allowed us to plot one curve, 7 in Lagrange, which had not been done at this, up to that time. And furthermore, understand the process, understand the quantity of attenuation. So at this point, let me just say that, move on to the paper here. And Steve Yabusaki, by the way, went on to work for Battelle Northwest in Richland, Washington, the state of Washington. And I believe he did retire. I called a friend of mine a couple of days ago that worked with him, and apparently he had also retired 20 years ago, and he didn't know where Steve was. But I believe that Steve worked his entire career, I could be wrong on this because I haven't checked it recently, with Battelle. The Battelle are big modelers in the United States. It's a big shop for modeling water quality, water quantity, and so forth. So that's Steve Yabusaki. Now, when Rosa Aguilar worked for us in the years 2012 to 2014, she went through all my classes, the 4 classes that I teach at the graduate level, plus the 5th one, the undergrad level, the open channel hydraulics, 5 classes in 2 years. And she graduated, and she heard me say basically the same things I've said to you. I haven't changed this class in 20 years. The content is the same. That's the way it is. And so when she finished, she got everything on the 1D and all the sorts of things that you heard me talk about. And at the end, I gave her a class on 2D because that's my style. I don't go deeply into it, but I do present the problem as is, as we saw it in the year 1981, which is when we published this. Okay, 6 months later, I got in touch on the phone with Rosa, just for the heck of it, we remain in contact. And I said, Rosa, she went to work with West, by the way, West Consultants in town. All of you know West Consultants. Our consultants, the consultants that are working with you are employees of West Consultants. And the people at West have worked with me, or I worked with them for many years, almost. I know those people for more than 30 years. Okay, so I asked her, I said, Point Blanca, what are you doing at West? And she said, Professor Ponce, I'm doing 2D modeling. I said, cool, that's cool. Yeah, I mean, you heard me talk about it, then you practiced it. Now, there's 2 issues here that we need to realize and understand. 98 to 99% of the people out there are going to be model users, and 1% are going to be model developers. And so the chances are that you will never develop a model of this kind. You may develop other simpler models, but not this kind. If you want to develop a model like this, first of all, somebody's got to fund you for a year or 2 to research what has been done to this date, not to the 1980, but to this date. And things must have improved, obviously. Things always improve. Research always improves things. Okay, so you can do that, but it would be very unusual for that to happen. Most of the time, 98 to 99% of the time, you're going to be doing like Rosa did, which is go out there in the field, the consulting field, and then they're going to ask her to run HECRAS. And HECRAS has steady flow, unsteady flow 1D, unsteady flow 2D, water quality, water temperature, I believe they added recently. And pretty soon they may actually even get to 3D, which is good. I mean, that's the progression of the thing. We started in the year when I joined Colorado State with 1D. At the time, we weren't doing 2D. And then 5 years later, Simons offered the Army Corps to do the 2D model. But it had not been done in the US. Very few people in the US were doing 2D models. So what was I supposed to do? Invent the whole thing? And so I talked to Dr. Chen, who was an associate of ours out there, and he said, Ponce, there's a report that has been written 10 years ago by this gentleman out of Rand Corporation. And basically, all you need to do is just follow what he did and improve it a little bit here and there, apply it to our needs and so forth. Because he was doing estuaries, and we were doing rivers. We were not concerned with estuaries. Our problem was the Mississippi, not an estuary. And it was not even in the estuary of the Mississippi, which, as you guys know, it must be one of the most complex estuaries in the world, the Mississippi. That's another subject, but while I'm at it, why? Why did Professor Ponce said that? Because the Mississippi is the river that has undergone more management of its sediment load in the last couple hundred years, a little more than a couple hundred years. Right after the founding of the Republic, in the year 1776, actually, no, it was in the year 1812. But since the year 1776, the Army Corps was involved. And I take that back. It was in the year 1812 that Congress gave the Army Corps of Engineers, which were the military engineers branch of the U.S. Army. They gave them responsibility for flood control and navigation. They wanted to give them responsibility for navigation only because they needed an agency that would be in charge of the navigation of the navigable waterways of the United States. There's a few, right? And the Mississippi was the grand one, the big one. But I guess I wasn't there at the time. But I guess the Army Corps said to the Congress, we can't do the navigation by itself. You got to give us something. You got to give us floods because We can't control the water and the river just for navigation and not floods. So eventually the Army Corps got the prize of both navigation and flood. So they are the ones that do navigation and flood in the United States. And that, I should say that, is for the foreseeable future, probably forever, because they already have it. Who's going to take it away from them? So that's it, okay? That's basically it. I was going to talk a little bit more about that, but let me just not do that because we're running out of time here. Let's go to the intro here. In this introduction, we basically said we're going to do this thing. We're going to do the two-dimensional model. So we basically ran the literature review. Every time you do a research, you gotta figure out what people have said. And nowadays, it's a little bit easy and complicated. Easy because you can go on the web. And I have said it in the past, and I'll say it again. If it's not on the web that you can pull out of Google or some kind of server out there that is available and can be found by Google, the stuff doesn't exist because nobody's going to go out there and do what we used to do a long time ago. We spent three months in the libraries researching all these things. In 1991, I believe, I spent the summer 1991 researching that paper on the ecology of the Pantanal. 3 months with students even. In 1980, that's 1991. In 89, we did the same for the base flow. But those times are gone. Nobody's doing that. The libraries, as you know, about 10, 15 years ago, they started to shut down basically their staff. They reduced their staff because they weren't using it anymore because all the consultation was on the web. It was already online. And they kept putting, over the last 15, 20 years, people have been putting their stuff on the web because they know that that's the way that it's going to be accessed. And of course, we rely on Google. Google is Google. They are the only game in town. Whatever they're going to do, and it will depend. I'm not going to say luck because I don't think it's probably luck. But let me just not say luck. But the point is that when you Google something, you as you know very well, it will depend on luck whether you're going to get it or not, because Google is going to make some choice and it's going to show you, like for instance, if you Google droughts, it will show you 20 million references. 20 million references. And how in the world are we going to do that? When we did the El Nino work in the year 2003, I remember I went on vacation. I used to go on vacation 2 weeks every year. So I told Shetty, who was working with me at the time, he was in town, he was from India. I said, Shetty, we gotta prepare, we gotta do this El Nino report. Everything that can be said in readable terms, in simple terms about El Nino. Don't get too complex because we're trying to reach the people, okay? And we're not gonna publish this on any journal. We're gonna publish it directly on the web. So you go out there and write a paper for us, for the lab, on this, and then when I come back, I'll clean it up. So sure enough, at the time, it was the year 2003, and he Googled 1,000 references on El Nino. And I believe he printed them, 1,000 references. And then he summarized those things in a couple of weeks, and he gave it to me at the end. And it was a very good job, and I think that was a very good paper, by the way. So Google is persistence. It is also a measure of luck. But eventually we get there. So, and I know you know what I'm talking about here. So we did the literature review. We, of course, have to mention Hansen, who is credited with being the first to outline the depth average two-dimensional formulation in 1961. He was out of Germany. Then Cupers and Broidenhill, working out of the Netherlands, Lendersee. Lendersee is the gentleman from the Netherlands who eventually, Lendersee wrote this paper in 1965. But then eventually he came to the United States sooner or later, a little bit later. I don't know exactly when he went. But we found him at RAND Corporation. And at RAND Corporation is where he published these two reports that are quoted in there, 10 and 11. What is the RAND Corporation? Maybe you guys don't know. The RAND Corporation is a think tank of the United States, and it is in Santa Monica, here in California. And I don't know, I'm not going to say anything at this point. Let me just say that they're there. They're still there. I know they're still there. They probably have had their ups and downs because they're a research agency, a research institution. And I believe they're private. Yeah, they're private. They're not governmental. So there's ups and downs in everything, right? But the RAND Corporation employed Lendersee. And Leonard C. wrote these two papers as an employee of a scientist of the Rand Corporation. Those papers, Professor Chen gave them to me, and I read them 3, 4, 5 times. I learned a lot of stuff out of Leonard C. at that point. I was very young. I was only, what was it, 31 years old at the time. Okay, so we applied basically Lenders's concepts, Lenders's model, which he, by the way, had borrowed from Kuipers and Broyden. I think it's Kuipers and Broydenhill and Hansen and others, right? People, researchers share information. They borrow information from other researchers. That's the objective. That's why people publish, by the way. You publish so that people can benefit from your research, and maybe they'll copy it. Sure. People have copied stuff, yeah. Maybe they'll copy it. I've copied a few things from Danny Fred, and he has copied a few things from me. And it's a feedback, so to speak. I talk about it, but that's just the way it is. Okay, so Kuipers and Broydenhill, big contributor to this subject. Then Vlokstra, also Dutch, also worked directly on this subject, and he made some important contributions to the issue of circulation. These were the first gentlemen back in the late 70s that worked on this problem. So the papers I was quoting were all middle 70s. Vlokstra's, I believe, is 1973 or 1974. Abbott, the great Abbott, Michael Abbott, I believe the founder and owner, I'm not sure if he has passed away. He probably has. I'm not going to kill him here. I don't know. Honestly, don't know. These people are 10, 15, 20 years older than I am. So this is conceivable they're still around, right? Rasmussen, I don't know. But Abbott is a great person, very well known in the field. He was considered to be the father of computational hydraulics at the time, by the way. Although I would put Conch right next to him. But Conch has a little bit less stature because Conch was an employee of Sogrea, while Abbott was the boss or the head of Danish Hydraulics, which is a big company. I believe Danish Hydraulics employs 100 to 140 PhDs around the world. And they have a lot of models that they sell, by the way. And I am told that they are expensive. Several years ago, 3 or 4 years ago, I was in Florida and for the evaluation of the Florida model. And they told me, the engineers out there told me that they've been running both the Florida model and the DHI, the Danish Hydraulics. I believe it's called System 22 or something like this. I'm not sure. Or the SHE model actually is kind of related to the work that Danish Hydraulics have done, because they are how can I say, they're a group out there, Danish Hydraulics and the SHE model. The SHE stands for, it's an interesting name, SHE, S-H-E. It's French for System Hydrologique European. I don't talk French, but it's System Hydrologique European, the SHE model, which is a model comparable to the Army Corps model HEC-RAS, right, comparable. Having not used the SHE model, I can't really give you the details because we really don't use it. You need a project to use the SHE model. Not only a project, you need money because those models are proprietary and you have to pay a lot of money, presumably, on the order of hundreds of thousands of dollars to run it, while the HEC models are all free. So that's interesting. Compare two things that are totally different. One is free, put by the U.S. Army Corps of Engineers, and the other one is proprietary, put by a group of top scientists out there in I believe it's Copenhagen, but I could be wrong. Copenhagen, Denmark, because it's Danish Hydraulics Institute. Okay, they've been around for 40 or 50 years. Okay, and they'll continue to be around, by the way. They're good in what they do. So we did work on the research on this, and we realized at the time that the fluid mechanics part of it had not been completed. And much as I hate to admit it, I'm not a fluid mechanics guy. I'm a hydraulics guy, which is different than hydrology. But I actually eventually ended up in hydrology and other things, but because of the teaching that I've done over the years. But I consider myself a hydraulics person. And so we we had a hard time with the fluid mechanics, and I realized at the time that that it had not advanced to the point at that time, by the way, 1980, 81, or actually 79 and 80, to the point where it could be said that we have closed the problem. Closed meaning finalize it. Nothing else could be added. We close the problem. It's a closed form solution, so to speak. It had not been done. And people had suggested that in order to take account of the effective stresses, and I'll talk about that later, that you could analog, model the effective stresses by an averaging routine. And averaging provides diffusion. The effective stresses were supposed to also provide diffusion. So if you cannot track down the effective stresses in terms of scheme, you could provide a simple scheme that would do the same thing. This is the kind of stuff that that was done by McCarthy in 1938 when he, by luck, I guess you could say, ran into the Muskingum and realized that it could do the diffusion wave, which of course McCarthy at the time didn't even know about the diffusion wave. The word diffusion wave came out in 1955. McCarthy was doing this in 1938. McCarthy just said, this is the equation and this is the way it comes out. It was only Conch 31 years later that said, actually, what McCarthy did was to solve the kinematic wave, only that he introduced numerical diffusion, and we can now calculate the numerical diffusion, and here it is. So that was a contribution of Conch, giving the McCarthy method of Muskingum a physical basis. And that's the thing about it. And the physical basis is represented by something that I'm going to repeat here today, and it is that the Muskingum Conch is grid independent, while the Muskingum is not. So the Muskingum will give you an answer which depends on the discretization. I mean, it'll give you whatever answer you want. If you want this answer, it'll give it to you. That's not modeling. While the Muskingum Conch is going to give you an answer. You may not like the answer, but it is an answer. It's the answer of the problem. So it's a better situation. Unfortunately, and I'm not going to sidetrack too much myself today. Unfortunately, the subject was complex at the time, 1969, 79, even 89, and a lot of people out there were not really understanding. And it was not until 1990 that the Army Corps endorsed the Muskingum Conch in their models, 1990. So it took them about 10 years to do that. And now it's there, and there's still people still talking about how to use it. Governing equations. So we talk about the governing equations here. These are the governing equations of our friend Lendertzey, by the way. I didn't change them. Conservation of mass, conservation of momentum, okay? And note in here that because this is a box that needs to be resolved, and the box is a two-dimensional box, the box is sold with shear stresses on the sides. This TXX, TXY, TXY, and TYY over here. Let me see, TXY, TXY, right, exactly. Because this is one equation, this is another equation. So we needed to solve these equations, but nobody knew how to do it. And people that preceded us had expressed by using fluid mechanics the shear stresses on the sides of the control volume as equations 4, 5, and 6. But the problem is these equations cannot be solved, or they're not determined, because they have turbulent velocity fluctuations in here, and they have this formula in here which accounts for the non-uniformity of the velocity distribution, and it's an integral between the bottom and the top. So these would have to be resolved, all of components, before you plug them back in here, and they hadn't been done at the time. So what we did, what people did at the time, and we actually borrowed from them, from the work of the Europeans, the work of basically Cupers and Broidenhill, they developed this averaging routine. And we knew at the time that an averaging routine, all it does is introduce diffusion. Let me give you an example. You have a student that gets a 95 and a student that gets a 65. The average is 80. Did the grade diffuse? Yes, of course, it diffused. Averaging is diffusing. So in here, we're averaging. We're averaging the local value is a function of the values in the neighborhood. Similar to what we did for the two-dimensional groundwater model. If you would recall, we did that for two-dimensional groundwater model. That was the equation presented in the paper by O'Brien et al. You remember that? I think you do. We also did an averaging. That was a thesis by the program that Jana da Silva put into her thesis in the PHP language, just an average. And it was so easy to program. That's why I gave it to her, because I knew that if it was difficult, she wasn't going to be able to do it in 1 year. So I said, well, if you have a year to do this, is easy stuff to do. And she did it. Okay, it took her a whole year because she had to learn from the beginning. She hardly knew anything until she got it into it, and she learned a lot in that year. She did the thesis, and that's the objective, right? So this is an averaging routine. Suffice it to say at this point that any averaging is a diffusion. And a diffusion, this is artificial because it's not supposed to exist. It's supposed to mimic the equations above, but we don't know exactly how good is the mimicking, right? We just know that it's some diffusion mechanism. So, and the alpha controls the situation. If alpha is 0, there's no diffusion, right? 1 minus alpha, if alpha is 1, no, if alpha is 0, there's no diffusion. 1 minus 0 is 0, so this value is equal to that value, and these values don't enter into the problem. But we typically would use alpha 0.05 or 0.1. We use 0.1. Give it a little diffusion. We also realize, by the way, at this point, we should realize that no problem out there that we care to calculate cannot live without some amount of diffusion. That's the function of the theta of the Priceman scheme. Set it up to 0.55 and you'll get a little diffusion so that you can work out the problem. If you set it up at 0.5, no diffusion in any situation out there that is going to go bad, like in the case of the round off, it's a matter of luck, but it will happen, then you're stuck. You have a problem that is unstable. It gives you garbage, trash, right? You can't present it to your boss. You can't say, oh, I'm sorry, I got this. It was the machine that was wrong. No, they expect you to come up with some answer that makes sense, it is reasonable. So this is what I'm going to say about the diffusion. Now, about the friction, we use this equation, which is now very familiar in our work, because we started this in 1976 by reinterpreting the work that Simons had done, the C over square root of G into the square reciprocal is equal to F, and this is our F. Only that we extended that to the two-dimensional domain. So the shear on the X direction and the shear on the Y direction over here. Can you see that? Extending it to the two-dimensional domain. We realized that had to be done. Originally, I thought that in my scant knowledge of the time, I thought this was going to be U squared into V squared, but we realized pretty soon that it wasn't working. It was not giving us the right answers. And then eventually I got a little smarter and I said, no, it's got to be this. Okay, it's got to be this. So that's the way we modeled the friction. The mathematical model was a model of Platzmann that everybody used at the time. It's called staggered grid. You have the depth, no, this is the stage and the friction, the velocity on the horizontal, or rather x velocity, y velocity, and the bed elevation. The bed elevation has to be determined in there. The difference between the circle and the x is equal to the depth. We're not modeling any sediment in here. Actually, I take that back. The objective of our model, original model that Simons put me in charge of, was to develop first the 2D water and then couple it with a 2D sediment. But for Yabusaki, I didn't want to complicate things for him. I said, circulation is your job. So you're only going to study water and how it circulates. So this is the concept of the water circulation. We actually never published that other paper. And the reason why we never published is because I moved to San Diego State and I got involved in many other things. I got into more teaching. I was busy doing teaching. You know, at Colorado, I was teaching 1 class, and here I'm teaching 3 classes. And even then, sometimes I taught 4 classes because I wanted it. And I said to the chair, I want these 4 classes. He says, are you sure? I said, yeah, I can do it. So for a couple of years, I taught 4 classes. 4 classes, can you believe that? That's a lot of work. I love teaching. At any rate, let's go back in here. So these are the equations, and I'm not going to go into detail of the equations, okay? But I should tell you at this point that there's a few people around the world that took these equations and gave them to master's thesis to develop. That's good. Many universities out there. There's tons of universities out there. And they're popping up more and more as we speak. Really. How many universities in the US? There's about 3,000 or 4,000. The last time I checked was 3,000, 3,500. Google it, of all sizes and kinds. The big universities, maybe 300 of them, but there's still 300, right? So there's a lot of universities people are looking for projects to do for master's thesis and PhD thesis. So these equations have been used around the world for people that develop master's thesis at the universities. So these equations, and we only did the x because the y we said it was the same, kind of the same. So if you're smart, if you can figure, if I gave you the x, then you can figure the y. You just change the direction. But you got to be smart. You got to be how can I say, sharp in the issues of numerical calculations. And this is what we're studying here today, numerical calculations. Not too many people could do it. Not too many people could do it. Numerical calculations are tough. Okay, so the results. We first, this is the channel pool baseline flow pattern. So you can see now the baseline. We finally got the thing to circulate. That was our objective. We had to show the circulation. Otherwise, Simons was going to say, I don't like this. Okay. We finally ended up doing both, the convection and the circulation. But we needed to discern when the model was going to convect and when it was going to circulate. Otherwise, we didn't know. We didn't know the essence of circulation, right? So we put this baseline together and it worked reasonably well. Look, we're using an alpha, which is the weighting factor 0.1. We needed to use a hefty, this is hefty already, because you can use an alpha of 0.01, 1%. But that's not hefty, that's not large enough to control the computation. This computation needs to be somewhat controlled. Otherwise, it will blow up on your face, and then you'll have nothing. These systems have a way of blowing up. Remember, the more computations, the more blowing up. I was trying to convince one of our students, I had a meeting recently overseas. I have some students overseas, that the issue that you got to strike a middle ground. You cannot make the mesh too fine or too coarse. If it's too coarse, it will be inaccurate. And if it's too fine, it will blow up. But that was something new that this gentleman had not heard before. I said, yep, it will. I can show you. You can test it. And then I explained to him, obviously, that they were because of two issues. The issues that O'Brien and et al. Had identified in their paper, in their milestone paper that we read extensively. That one of them is the truncation errors, and the other ones are the roundoff errors of the computer itself. The CPU has errors in there because they have a certain word length, and the last digit of the word length is an approximation. They have to cut it somewhere. And that stuff could actually, that small error, eventually, under the right conditions, could mess up the computation. We know the origin of that stuff. Okay, so we have in here, when we found out that if we neglect the convective inertia terms, and you can do that readily in the model, you say, well, we got 7 terms in here, drop 1, put a 0 in front of it. That means drop it. And what would happen is that it would convect, it would not circulate. Can you see the difference? This is circulation. And this one is the same problem, only without convective inertia, right? This is interesting because it can be readily compared with a one-dimensional case. In the one-dimensional case, circulation basically is diffusion because the equations are set up in such a way they have to be second order. The equations are second order, and they circulate. Basically, in 1D, diffusion causes, second order terms cause diffusion. And in 2D, second order terms cause circulation. So circulation could be defined or could be described as the way the model works in 2 dimensions, because there's x and y, not just x, as you know. So we proved that, in fact, what Flockstar and other the previous researchers had said, that if you neglect convective inertia, it's not going to circulate. It's going to convect and not circulate. Now, why would you neglect convective inertia outright? And the answer is, at the beginning of computational hydraulics in the 60s, 50s even, people were neglecting stuff because they couldn't handle it. Don't forget that Fred did that. Danny Fred, when he did this 1974 paper, which I read extensively in order to do my own, he neglected a couple terms because he couldn't handle them. He said, "Well, we're not gonna get a complete answer. We're gonna get an answer nevertheless." So people were in the habit, or I guess in the custom of, if a model, if a term was not to our liking because it was causing difficulties, we would drop it. So that's the issue. That's why we here drop it outright to see what happens. So we basically came out confirming the conclusion of various researchers prior to us, mostly in Europe, by the way, because in the US, this had not been done yet at the time. So that was basically it. So now we proceed in here. Okay, then we try a different configuration. This is what we call the expansion model. We knew that it would circulate over here. Okay, but then we didn't know about this. And other people in the literature had used this. Abbott, as a matter of fact, had used this configuration. So we figured, let's see if it does circulate. And it did circulate under all conditions. It's the same process. As you can see, we didn't, these figures here were generated by the computer. We wrote a little code in order to velocity vectors had to be drawn with their respective angles, right? And we did that. That can be done. It's done all the time, by the way. Nowadays, we're looking at 40 years later. 40 years later. It's a side story. I remember, I should tell you this. We wanted to print all this stuff, and at the time we did this in the 1977, 78, we didn't have a printer. So I applied to get some money for the for a printer to use in our group. We had a research group, and I paid $17,000 for a printer. $17,000 for a printer that does things that now you would pay 500. But that's 40 years later. Okay. But at the time, there were no printers. The printers were scarce. I mean, they were beginning to develop the printers. So at the beginning, let me say, we paid $17,000 for that printer. And we bought it and we used it for a couple of years, and then we had to give it away because it had become obsolete. In the process of my career, by the way, 50 years, a lot of things that I've done have become obsolete in the middle of it. One thing though, Fortran never became obsolete. People have tried to kill it, but they could not, and they will not, because it still remains the best calculator as far as speed is concerned. But the rest of the stuff, a lot of stuff became obsolete. I can tell you, I'm not going to sidetrack myself on it. But there's a lot of things that became obsolete. 5 years enough, it becomes obsolete. People have to retrain, use new things, and so forth. That's just, as I say, the nature of the beast, because technology constantly evolves, and we have to adjust to the new technologies. Okay, so we got in here. Then we said, well, what about if we reduce the delta t, or the delta x rather, to 0.5 meters? If we reduced it, and we came up with the same answer. A little bit thicker resolution, but it was okay. So basically our evaluation was, we say in here, we try this model under any and all circumstances of data, but we couldn't discuss it here all. But the Yabusaki thesis does, though. The Yabusaki thesis is a 300-page report, and basically this paper is a summary of his report. So people that are interested could go and get the Yabusaki thesis. And how to get the Yabusaki thesis, that's a very interesting concept because it's not posted. I have it. I have a copy of it somewhere. But I guess people, you could get it if you wanted to, you could get it, because there's a system called interlibrary loan, which I believe is a great system. It used to work very well for all of us. If there was a book out there in Australia that we wanted to get a hold of and that we couldn't get, interlibrary loan system first asked all the registered libraries, 300 of them in the United States, if they had it. And if they didn't, they go directly to Australia to find it. And they will bring the book and loan it to us. That was a good system that worked, and I believe it must still continue to work, but at a much reduced level because people are not doing library technical, on-site library research anymore because of the influence of the web. Okay, so over here, I'm going to discuss in here This says results for the testing program are reasonable and encouraging, despite the presence of two flaws traceable to the representation of the effective stresses. Don't forget that our objective was not to break, how can I say, break new ground in here in terms of the modeling itself, or how do you construct a model. Our objective was to determine what is it that is causing the circulation. That was our objective. That was the focus of our research. The first issue, among the various issues that we raised, was that the circulation was caused by the convective terms. Because if you drop the convective terms, there was no circulation, and that was confirmed. No circulation if you drop the convective terms. Okay, so that was good. That was a first result. However, that result had already been identified by Flockstra in his work. So we just confirmed what Flockstra did. So we're looking for something more to make our effort worthwhile. Okay, so the first flaw is there have yet to be found a physical basis to choose the appropriate weighting factor. So we were using 0.1 because that seemed to work good. It was enough to produce stability and not enough to obliterate, or not big enough to obliterate the answer. Because as you know, like in the theta weighting factor, if you use 0.6 it's good, but if you use 1, it starts obliterating it. We showed that already. It starts like, it's like you took a whole bunch of aspirins, like 10 or, you know, I don't know how many aspirins you have to take to kill yourself, but 10 aspirins is a lot, and then you will go around like a zombie, you know. You've been doped by the aspirin. The same thing in here. If you increase the alpha high enough, like 0.7, 0.8, it will start doping, meaning it will start obliterating the answer. That's exactly the way it's happening, or would happen. That's just the way it is. It's in the nature of the numerical scheme and everything we work. And that's the good thing about this class, is that we're teaching all the ins and outs of how these models work. Because technically, when people use HEC-RAS, and anybody can use HEC-RAS because it's free. You can download it and you can start running it. If you have the wherewithal to read the 2 manuals, and I don't know how many people read it. I presume those are very serious, have to read the manuals anyway to understand the model. But a lot of people don't have the time or whatever, and they really don't know what they're running and what answers they're getting. That's a fact. I can tell you stories about that. You know, people out there that are not engineers, and they're running HEC-RAS. They're geographers, or they're something else. Not even geographers, they're something else. Okay? It's interesting, this geography issue, and I don't want to dwell on it because it's kind of a sticky issue. But the other day I got a reference from some gentleman over there in the world. I believe he originated in some country of Europe. He's written a paper, and he's a geomorphologist. And he wanted me to look at it because he said that he had learned from the Vedernikov, and he thought that it was useful, the work, what he had learned from our papers on the Vedernikov in the S-curve. And he wanted, just for the heck of it, he was working on the paper, and if you can take a look at it to see how it is, where I am, and so forth. And then at the end, he says something interesting, which I'm going to quote or convey to you. He said, and keep in mind that we're not using too much math because I want to publish this in the Journal of Geomorphology or something like that, some geomorphological journal. And I can't do a whole lot of math because the readers would not understand it and they will not publish it. How fascinating. So that he confirmed what I had already all the time believed. If you cannot study, or if you do not study calculus in your curriculum, don't expect to solve calculus problems later on, right? It's obvious. So there is trends and levels of utilization of technical matter. There's always like that. Okay. The second drawback is a weighting factor. As the weighting factor is increased, the model reacts as if the fluid is becoming more viscous. As you can see, more viscous, more diffusivity, okay? Increasing the exchange of lateral momentum and increasing viscous damping. That's what I said already, viscous damping. So basically, one should not abuse the weighting factor. We already know that. One should not abuse the weighting factor. The weighting factor is there to help us, but don't abuse it. The best thing to do is to try running a weighting factor, the minimum that could be run without any problems of stability. Remember, I told you, and I'm going to repeat, If a model runs for 24 hours, it's probably no good because it already has a whole lot of diffusion in order to run for 24 or 48 hours. CPU time, I'm not talking about real time, but CPU time, 24, 48 is too long, you see? And that means the answer is no good. Well, of course, if you don't know what the answer is, then it's a problem because you don't know what you're doing. You have to have a sense of what, more or less, what the answer is. What is modeling? And I'm going to state this once and for all. Modeling is not done to get an answer. If anybody wants to get an answer out of a model, he or she is wrong. Modeling is done to get a range of answers. What if? What happens if I do this? I get this. What happens if I do that? I get that. Oh, right. I'm modeling. I'm studying the process, and I'm learning from the answers that the model is giving me. I'm not looking for one answer, because that means I will have to know precisely what all the parameters are. And we don't know that. We really don't know. Don't know exactly the parameter. We don't even know the Manning's N, the exact value of Manning's N, let alone anything else. We don't know the alpha and so forth, right? So modeling is a way of studying, because you can study without a model, but it will be difficult. You can't concentrate on the subject. With a model, the model is actually helping you to get some thoughts into it so that you can really solve the problems that you have. So that is modeling. If you have learned anything in this class, it is this, very important. What is modeling? Okay, so model displays at least two instability mechanisms, nonlinear and Courant. If there's nonlinear, the nonlinear instability comes from the fact that the equations are nonlinear. So they're going to generate nonlinear perturbations in there, and if these perturbations are small enough of the size of the grid, then they'll drop, and eventually we drop. Courant instability is more like in the construction, the macro construction of the scheme. So the Courant law will say the Courant's got to be greater than 1, or the Courant's got to be less than 1, or whatever. In this case, for instance, the Courant, I believe, has to be less than 0.5. It has to be less than 0.5. Unusual, right? Usually the Courant is less than 1, but that was for 1D model. For 2D model, in this case, we tried this, and we considered the Courant has got to be less than 0.5. How will we get, right there, it says the Courant might be less than or equal to 0.5. How do we get to that answer? Or how would we rationalize this answer? It's not 1. It's not maximum or less. The answer is you would have to run, this is interesting, you would have to run the von Neumann technique on these equations. And then from there, try to analyze what the Courant for stability would be. And I'm pretty sure that it will say 0.5, because we have tried this model with 0.6 and 0.7, and it will blow up quickly. You know how its instability could be fast or it could be slow. The fast instability is related to Courant. The slow instability is related to the nonlinearities, which are always there. Nevertheless, we need to control the instabilities because an unstable model is of little, actually, it's no use. You're not going to do anything with an unstable model. So you got to control the model. Conclusions. Major conclusions are effective shear stress modeling is a necessary condition. So we have to model the effective shear. Now, we can model with a surrogate, but we still model it. Convective inertia must be included in the analysis where secondary currents are being considered. Yes, positively, as found by Flockstra originally in the early 70s. And here it is, the crux of the matter here. We decided to do this, to look at scale. Why? Because I am very familiar with the issues of scale. We've dealt with scale all my professional life. And I said, what happens if I don't use 1 meter as the increment, the space increment? What if I use 100 meters? What's going to happen? And that's very easily done. You just tell the model, you know what? Don't use delta x 1 meter, use 100 meters. That's easy. Bam, that's it. Gives you an answer. Okay, what happened was that when you use 100 meters per grid, that's a huge model, right? It's more like in the ocean. It's not river, right? Because the ocean is expansive while the river is kind of narrow. So in this case, we got no circulation. No circulation. We could not get circulation in the large model. And so therefore we studied this and we concluded that the circulation is based on the terms that are gradients, not on the terms that are values. And the friction is a value. There's no gradient on the friction. The friction is that, and that's it. While the convective inertia is based on gradients of the velocity. And the gradients are the ones that cause diffusion and therefore circulation. So friction doesn't cause diffusion. Hey, that's very interesting because remember on the 1D model, when we said that you have a kinematic wave and you don't have diffusion? Remember I said that? Remember Dave Vasco when he gave a presentation, I believe it was in Maryland, 1980, I don't recall exactly what year it was. I think it was 78. Dave stood up in front of the group or the attendants to the conference, and he said that friction caused attenuation. So I called him later in a corner of the room and I said, Dave, that's not correct because the kinematic wave is based on friction and does not attenuate. And that's when he says, oh, I got to look into this a little more detail. And it is correct. Attenuation is caused by interaction, not by one value. We know that now because of the S-curve. The S-curve has told us that. What is attenuation? What is it caused? That was in the 1D model. But in the 2D model, the attenuation is caused by the gradients. And the gradients are in the convective term. The spatial gradients, by the way, they are the convective terms. So we finally got to this conclusion. And I stated at this point, it says a competition exists between the convective inertia and the resistance effects. Barring wind forces, right? We're not using wind forces in here because we were looking at rivers. In rivers, there's no wind because wind needs what is called a fetch to develop, and the fetch has to be long, miles. In rivers, you don't have miles, usually in one direction. Like in a reservoir, you would have miles in one direction. So reservoirs, how to generate a wave that would overtop the dam, that is an issue of what is called a fetch, F-E-T-C-H. But that's not applicable in the case of a river situation. And we were concentrating on rivers. So there's a competition exists between convective inertia and the resistance. These two components of the equation. Barring wind forces means we don't consider wind forces because wind can also cause circulation. But that's in the estuary, not in the river. Circulating flow is possible only when the bed resistance is of minor influence, that is, at small length scales. In other words, at large scales, it's like the kinematic wave. Bed resistance takes over the process, and therefore there's no circulation. Okay, the no-slip velocity is not absolutely necessary. At any rate, that's a secondary conclusion. And the type of boundary condition has a significant effect on the resulting flow patterns. Boy, what a statement. That's a truism. You cannot solve an equation, any equation, by just considering the interior points. Because the boundary conditions are going to affect. You have some kind of boundary condition out there. You have to have. In mathematics, in advanced mathematics, there's two conditions. There's the interior points and then the boundaries. In the interior points, if you don't consider the boundaries, the interior point gives you a characteristic solution, a typical solution, but it does not give you the solution. In order to get the solution, you have to get the boundary conditions in there. And that's how we saw the S-curve as a characteristic equation. So we didn't use any boundary conditions. You didn't hear me talk about boundary conditions there. So what we came up is with the norm, the general aspect. We were not going to take account of any details, which were going to be given by the boundary condition. We eliminated the boundary condition from the problem. And we got a whole lot of details, but in the sense of the problem, not on the overall details. So the details and the boundary conditions come about when you actually apply the model to a certain case. At that point, you define what the boundary conditions are and you proceed. You will remember that in the case of the groundwater model, we had all kinds of boundary conditions, flux conditions, stage conditions, mixed conditions, and so forth. And calibrating a groundwater model is no easy task. It requires a lot of experience, time, practice. Fortunately, when we developed this model, I had Mr. Shetty, who had come from India, and he had done a lot of calibration, a lot of model groundwaters. So he was able to help us with the calibration. I myself would have not done it because I didn't have the practice to do it. I just knew how it was done, I knew how the interior point differentiation was. And I had some sense of what to specify for the boundary conditions in that problem. but I had no idea that the calibration was going to be difficult. And he did it. It took him a while, but he did it. And we, in the other class, in environmental hydrology, tomorrow we're going to talk about that. Briefly, of course, because environmental hydrology is not supposed to cover those details, but we're going to talk about it briefly when we talk about the Ojos Negros project that we did in the year 2003 with Mr. Shetty over in Baja California, Mexico. Additional studies are needed in order to identify the numerical effects of various discretization schemes and techniques used to represent the physical boundaries. Right, the physical boundaries. So basically, we answered the question that we were about to. We said convective terms, you need to not omit them, not neglect them. But this issue of the scale was, I believe, new. And we came up with this, and that's the reason I think why we published this paper. That was a new part. And I should tell you at this point, repeating what I have said before, that if you want to publish in a journal, you have to have three issues here, three components. You have to be, how is it now? You have to be correct. You have to write the paper correctly in English language. If you miss the English language, they'll throw you out. They'll say he or she doesn't know how to write. Get out of here. Okay? And the third one is it has to be new. Because if it's not new, they say, the reviewers say, you know, this has already been done. Go back and research the literature or something else. So it's got to be, again, it's got to be well done, precise, good. It's got to be new, and it's got to be language-wise correct. Those three will get you the success that you need in order to publish. If you miss one of them, you're dead. And it happened to me, by the way. I told you I published 52 papers, but I wrote about 70 at the time. So 19 of them or 18 of them would not have been published for whatever reason. Either I missed one of those three, or else I was unlucky. And I ran into some reviewers that didn't know their subject, which happened. I already told you that a couple times, not too many times. Overall, the system works, but sometimes it had its problems. Sometimes it fails. You don't know. You can persist, but only a certain amount. Because if you persist too much, it will backfire. And that happened to me also several times. Eventually, you can even get into a fight. I mean, not a physical fight, but a fight with whoever's reviewing it. Because you feel you're right and they don't feel you're right and so forth. You know, that's just the way it works. But the point is that those things need to be considered. Although not directly benefiting the formulation, the compilation of physical data on various circulating flows would certainly facilitate the development. Basically, we're saying we should know more of the physical process in the field. Never, let me give you a recommendation. Never miss an occasion to go to the field. Because it is in the field where you will observe, you will raster into your mind. Because the rest of the stuff that you read, even on the web, it's all vector information. And vector information goes in and it goes out. Everything you learn in this class, in 2 years, they haven't said this has been studied. You will remember 3% of what you learned. What I said, you will digest it and remember it while it's good for the exam. But a month, 2 months later, the mind is like that. You will remember 3 to 5% of what I said. And that is your education, because you're better than anybody else that didn't take the class. They don't know the 3 or 5%, you see? Because the mind is limited. There's only a certain amount of stuff that we could accumulate in the mind. And memories vary. Some people have a lot of memory, others don't. And furthermore, you know, memory also changes with age, as you know very well. I'm not going to get into that. I'm already getting in there, by the way. So let me just say that at this point, I have finished, and I have a few minutes here, and I do want to say that as a personal note, I have enjoyed this class. I always enjoy this class. I've taught it for 40 years. Every couple of years, this is the 20th or 21st case, I think, or 21st time that I've taught this class. And at the beginning, we had about 30 or 40 references, and it kept increasing every year because we kept publishing. And now we have about 60 or 70 references that I use. 80% of them are mine because, as you know, Professor Ponce has published a lot in this area. Luckily, we got good training at the beginning and we kept doing it. The S-curve was something that I did. Um, it was just luck. I was at the right place at the right time with the right kind of people. And I knew that this had to be done because I knew the von Neumann very well because I used it. I learned from Kunsch. I also knew the Saint Venant, which has been known for 150 years. Everybody knows the Saint Venant equations, how you put it together. But they couldn't solve them. So then I said, let me try this. And I did it, and I solved the Saint Venant equations. Not completely, because it hasn't been done yet. But we solved it in a linearized way. So we ended up with half or 60 or 70% of the problem. But more so, we explained the issues of diffusion, which was not known at the time. See, Danny Fred did not know that. He did not know that his dynamic wave model that he was pursuing was so diffusive to the point that it would not even exist. And Leggett and Whittam, he did his work in 1973, and Leggett and Whittam did their work in 1955. So that was 18 years earlier. Leggett and Whittam had already said that. Interestingly, they know. They said in their paper, in which we have briefly read the Leggett and Whittam paper, they said, you know, these dynamic waves are so dissipated that they may actually diffuse very quickly, and the mass goes on to form to add to the kinematic wave, which travels much slower, comes in the back or at the end, rather behind, and the kinematic wave is benefiting with all these dynamic waves that are diffusing instantaneously. They diffuse instantaneously. The momentum is diffused, but the mass does not disappear. The mass has got to go somewhere, and it goes on top of or in the middle, or it forms part of the kinematic wave. So Leggett and Whittam said that in 1955. And yet Danny Fred, in his wisdom, I guess, insisted in 1973 that he was going to calculate the dynamic wave. And he did. But most people don't run a dynamic wave. Because like I already told you, the dynamic wave diffuses so much that for design purposes it's not necessary. You don't want a wave that diffuses, unless, of course, it is a wave from a dam breach. That's an exception. Everything has an exception. In a dam breach, you want to know how fast it'll dissipate. Then you're justified in using the dynamic wave. When Danny Fred developed his Groundwater Model in the year 1978, he immediately followed up with his dam break model in the year 1980 or 81, because he realized at the time how fascinating that nobody was interested in the Groundwater Model, but a lot of people were interested in the dam break model. So he used it throughout the 80s, and throughout the 80s and even 90s. The dam break was the model to use for the dam breach problem, because that was the only one available that Danny Fred had put together based on his dynamic wave, which was good. So it served for something. But then eventually he was superseded by the Army Corps, which had a better shop, better, not support, I wouldn't say support. Just the Army Corps is more accepted around the world, the Army Corps of Engineers. Danny Fred was the Bellsville lab of the National Weather Service. Who are those guys, right? So there, I'm just saying to say that. But the point is that eventually the Army Corps model, CLEC-RAS, overwhelmed the NWS, the dynamic wave. They overwhelmed it. They took it out of business. Business, I say business, but it's not really business because they weren't selling their model either. National Weather Service is an agency of the US government. But the Army Corps took over. Not only did they took over, but um, Danny was in charge, and he passed away in the year 2008 or 9, I believe. And I don't know, and I'm not going to explain or express anything in here, but I surmise that after he passed away, or at about the time, the interest was lost, and I believe people are not using dam break anymore. They are using CLEC-RAS, which prevailed. So with that, I am going to consider it done tonight. And again, I do repeat that for the exam, I may ask questions on this paper, but only on the stuff that I discussed extensively. I have discussed extensively the issues of scale and so forth, how this whole thing was created from the beginning, the history a little bit. I didn't get too much into the fluid dynamics because I know that you wouldn't probably handle it. And neither I, for that matter. It's been a lot of time. It's been quite a while since I've dealt with these 40 years, as a matter of fact. As a matter of fact, we published this paper in November 1981. The original version, November 1981. So this paper just barely is 40 years old. How about that? November 1981 is the publication of this paper that we just read today. And today is December 1. So for one day, we missed the 40-year anniversary of this paper. It's a great paper. I love it. And I hope you enjoy it when you reread it for the exam. So with this, I'm going to wish you a good presentation next week. And remember, don't exaggerate the number of slides. 15 would be fine. 10 to 15. People don't want to be loaded with a whole lot of stuff. People don't want to be, this is a presentation which is supposed to be kind of informative. It's not really for study. One thing is information, another one is study, by the way. On my website, I have divided my videos on 9 categories. And the first category is informative. It's easy. Everybody can read it. Everybody can understand it. The 7th category is so tough that I reserve it for only my grad students to read. You see, so you got knowledge is like that. It's at different levels. The same knowledge could be repeated in 3 different ways to 3 different audiences, by the way. And that is the reason why Donna Tisdale in the year 2006 hired me to water down the stuff that had been put into journals so as make it readable for the politicians, because she said the politicians couldn't read it. They refused to read it. And they are the ones that command, right? They have the command. They have a decision-making power. So we got to convince the politicians that we're right. And they won't be convinced unless we give them a story that they cannot understand. And I stress, they have to understand it. And it's difficult to get people that don't have the training to understand the stuff that we're talking. With that, okay, if any questions out there, otherwise, I'll see you next Monday. The lineup is already set, so we pretty much ended up in here at the right time. Thank you very much. So at this point, I'm going to say goodbye. See you next Monday.